a set is disconnected if and only if there exists two open sets, U and V. And by the way, just to quickly define what open means here, if we have a set that looks like this, then open means that we can pick any single point inside the set, let's say here, and there exists a positive number epsilon such that the ball in the space around that point with radius epsilon is totally contained within this set. So to define it more formally, well, to just write down.
This is complex analysis, but this is also topology, right?
Maybe. So a set is open. Well, let's give the set a name, like, I don't know, X is open if and only if for all little x inside X, there exists some positive real number epsilon such that the ball of radius epsilon centered at X is totally contained inside the set X. Alright, so that's the definition of open in formal terms. A set S is disconnected if for every open, well, not for every, well, if there exists, I don't know why I said for every, that's the same thing as for all, there exists open U and V such that the intersection of S, U, and V is equal to 0, and S is contained in U intersect V. Additionally, with the requirements that S intersect U is not just equal to S, and S intersect V is not just equal to S. You know why? This is a get out of jail free card, because if I have V and I have U over here and I have a set S inside it, I don't know why I put intersect to be union, and I have a set S inside V, as you can see, it's totally inside V. It's all connected, it's not disconnected at all. But as you can see, it's in the union of U and V. Does that mean that this definition works? No. So we have to make sure this is true. So that's what it means to be disconnected, and to be connected is just the converse of that. So one short exercise we're going to do is prove that an interval is the only structure in R, or the real numbers, that is fully disconnected. Whoa. So we have the real line, and now we're gonna take one point and we're gonna take another point. So what's the definition of an interval? A set I, which is part of R, is an interval if and only if for all x, for all x and y in I, or, okay, let's put it this way. If and only if we pick x and y inside our set I, x distinct from y, such that for all x is less than or equal to z is less than or equal to y, or vice versa, z is in I as well, which basically means, in short terms, that if 2 points are in a set and are in our interval, and we have something between them, then that point is also going to be in the interval too. Well, an interval is obviously just a region of space stretching from one point to the other and including everything in between. And of course, these don't have to be the endpoints of the interval. They could just be in-betweeners too for the real endpoints of the interval. All right. So, once again, we have the definition of an interval right here. So now, how can we prove that an interval is the only connected thing? Well, I'll leave the second proof that if a set is an interval, then that implies connectedness. I'll leave that for next time. But today, we're going to look at if something is connected, it's going to have to be an interval. That's the one I want to cover. Let me think about it for a second. Oops. Yeah, I'm pretty sure it is.
Yeah. Baby, can you go to that boat?
Okay. So now, to prove that, let's say we take some set K, right?
Sure.
And K is not an interval, which means that for some xy in K, there exists a z in between them such that, well, z is not in K. Pretty simple. So that's the converse of being an interval, not being an interval. So how can we essentially prove that if K is not an interval, it has to, well, be disconnected? So let's see. If K is not an interval, that means that at minimum, K is an interval with 1 point in the middle removed. Like, let's say we have the whole real line here, and in between, so it goes on and on and on. But in between,
What is the name of the song? It goes on and
I don't
on.
know. No, seriously, I don't know. I want to know it too.
Yeah.
So let's say K is just an interval with some amount of points removed. Because at the end of the day, everything is an interval, or an infinite interval technically, with some amount of points removed. It can be a finite amount of points, as in here, or an infinite amount of points. So at the minimum, let's say K is a regular interval, but with 1 point removed. So let's say that point is right here. It's the interval from A to B, well, it's open, so, excluding Z, or let's say C. That's usually an intermediate value between A and B. So this number right here is C, the little break in it. So, obviously we know something's disconnected if it can be covered by two sets, two open sets that are each other totally disjoint. So, let's say, we have set A, which is described by negative, well, technically not. negative infinity to, what's the right half? A, and it has to be open, remember, intersect K, that's one of our sets, and the other open set is going to be C, well, yeah, it's open, so that still is legal, to positive infinity. Now, of course, the intersection of an open set and another open set, which is why we had to make sure this was open, is an open set. Same thing here, which means that, well, now we have two open sets described that cover the entirety of K without each individual one covering the whole thing. Like this doesn't cover the entirety of K, and this doesn't cover the entirety of K, and their intersection is the empty set, but together they cover the whole thing. I mean, it's like, how can I explain it? Nah, that's not a good analogy. So I'll just leave it as is. So we managed to come up with two open sets that individually didn't cover the whole thing, but together cover the whole thing and are each disjoint. And of course, if I slice it up, I remove another point, let's say D. Now we have three open sets to describe it. Minus infinity to A, C to D, well, I don't think we even need to intersect K, and D to infinity. And then we can keep cutting it up. If there are infinitely many points removed in a certain section from, let's say, C to D, I mean, we can do the same shenanigans. We can just say, oh, I don't know why I put this. We can just say, yeah. Okay, we have minus infinity to C and D to positive infinity. So there we go. We have now shown that if something is non-interval, then that means that it is totally disconnected via our definition of disconnected that we came up with all the way at the beginning of the lecture. So that's it. Thank you everybody for watching.